Vijay, you can start, I guess.
Okay. Yeah, so welcome back to part 2 of this tutorial. I had a quick...
Vijay, 1 minute. Vijay.
Can we turn your laptop around so you can see the audience?
Okay.
Just carefully lift it up. Vijay, we want to show you the audience.
Oh, okay. Let me see which...
Can you see? Hold on. I have to start video.
Oh, great. A lot of people. Perfect.
They're waving at you.
Okay, I don't see that, but I believe everyone. So yeah, hi.
I don't know, waving or saying goodbye to you, Vijay.
Okay, we can start now.
Okay, great.
Let the video be on, then we can see what's on the screen.
Okay, yeah, but welcome back everyone to this part 2 of this tutorial. So I had a very quick chat with my co-presenter during the break because we have a lot of things that are yet to be covered in the next 1.5 hours. So we decided to curtail some parts of this tutorial, but everything is there in the slide. So I was going to cover now a review of some of the common waveforms that are used by radar and communications from the perspective of joint radar communication technology. So we were going to look into radar-centric waveforms that may also be used for joint radar comms to give for communications functionalities and vice versa. So we would skip this part. I'll be around if there are questions, but when Bhavani covers bistatic ISAC in later in this tutorial, then he will give some overview of some of these waveforms. For the rest of the tutorial, we will be using customized waveforms. So a lot of discussion that I was going to do while covering these standard waveforms may be redundant. So we think we can skip this part in the interest of time, but as I mentioned, everything is there on the slides. And if you have any questions, I'll be around. You can also email me later. So I guess, Bhavani, you can start with the widely distributed radar segment in this part 1, and then we move on to the part 2 on applications.
Okay. So we will quickly move to widely distributed radar. And the idea here is that the is that the transmitter and the receiver antennas are not co-located, so they don't have the same oscillators, etc. But more importantly, for each transmit receive pair, it sort of sees a different target. So for the ideal target is a point target, or a small sphere, metallic sphere, where you get the same reflection from all wherever you look at it from. But typically the targets are not like that, a metallic sphere. So you would get different reflections from different angles, depending on how you look at it. So that sort of gives you a thing about target diversity. So maybe the target is not reflecting.
This got clipped off for the virtual attendees. The presentation is clipped off for the virtual attendees. Yeah. But please come. Yes, sir. I think
Because then I used the slideshow here, because that was the thing that we used previously.
no, there is no display. Actually, there is no pop-up yet.
The pop-up is there.
It's there, but we're not able to see it yet. I'm going to presentation mode. What do you say? Yeah, okay. Yeah, it's not.
I click on it and then it will flow. Click on it.
Here, there is no pop-up yet.
Go to that location where you see that.
Yes, sir. It's going inside there. Actually, the back side of the box. Just give me a second. Just give me a second. Sorry. So sorry, sharing.
This name is on the windows, you'll see that.
Oh,
Droplet. Go to the top. Go to the move that away. Yeah. Go to that other one, display thing.
Yeah.
Then click it.
this presentation. I think so there is a presentation. I know how to share screen. Stop sharing screen.
Okay, now if I use this, is this fine now?
Still click top. Yes. Okay. This one.
The other thing is, Vijay, maybe if you want to share, then I can ask you to move on. It's faster this way. It is working on your side.
Okay, let me try that.
Yeah.
So you share, Vijay.
Okay.
Yeah.
Oh, I should automatically.
Yes.
I need the video, right?
Yes.
Okay, I'm going to share Bhavani then.
Yeah, okay. I have only a few slides, then we'll take over. So it's easier. But you don't need the spotlight, or should I change it? Or
You can click remove spot. Yeah, you want to have it? Okay, fine, then
one means fine. I think it's easier to see the whole screen. You've seen me enough already.
virtual audience not see.
Okay, but it's fine, I guess, right? Okay. Vijay, next slide, please. Okay, so now, yeah, in this case, for a target, it looks differently from different angles. So you become more like a statistical MIMO here because you would have the target modeled as random variables here, and then you would use some sort of diversity to sort of classify or detect a target. So you could sort of collect information from multiple angles, multiple directions, and sort of get this detect the target. That's the idea here. Vijay, next slide. If you look at, I was mentioning about the previous slide, it was mentioned about stealth targets, but even for simple targets like the car, if you put it on a turntable and then you look at its scattering, there are a few parameters. In certain directions, you get a lot of scattering, and in some other directions, you get minimal scattering. The same is for near field as for far field, depending on what you want to use. And the point here is that these are in radar, you have the concept of point targets and extended targets. These are not point targets and not isotropic targets, so they're extended anisotropic targets. So you have different information from different angles. Next slide, Vijay. Not only a man-made object, but even a human being has different RCS depending on where the radar looks at. So, so it becomes important that you don't have a monostatic radar, or you would have a sort of network of radars. So each sort of probing different angle of the target, and then sort of combining this information to present a coherent target. Next slide, Vijay. So here is the quick problem set up, or the things that we want to look at. So you would have a target scene where you have some number of radars here, and then this would be the sort of delay between the transmit and the between the nth transmit and the mth receive, and then PK is the kth target location, and then this is the classical path delay, and then you would have the Doppler, which is sort of projected onto the direction, the radial direction here. And so this would be the Doppler frequency that you would see in each for the mth pair. One thing that we should notice here is that when you have multiple radars sort of looking at it, and then if there's a single target, for sure there's one target, you could somehow combine information. But you have multiple targets with multiple radars looking into it, you don't know which information corresponds to which target. So there's always this problem with data association. So you have to somehow, figure out from each target pair, for each transmit receive pair, what this information pertains to, and then fuse them accordingly. So that is sort of a difficult problem. So we sweep it under the carpet and move on. With the next slide, please. Okay, so if you sort of, now we come back to all the equations from henceforth. So you sort of, here is the model for the nth receiver after carrier removal. We are interested in a single target here. As I said, multiple targets removed from the scene. So if you have single target, I want to know the position and the Doppler, and this would be the reflected signal from the target. Look at the thing here is that this is a receive signal. You would have the transmitted pulse, the Doppler, and then here is the distance from transmitter to the target to the reflection, the target to the receiver. This is the amplitude. So the amplitude is already quadratic in distance. So if you go to the power, it becomes fourth power. This is what I was trying to tell you for the radar. And then you collect all the wanted and unwanted, known and the unknown information. You could actually come up with an expression like this. The received signal it would be sort of put here in this vector R, and then you would have this matrix here which has the information about the delay Doppler, and then you would have you'd have the other things here in this vector. And then the idea here is to sort of using this equation try to estimate theta. What we do here is we not do the estimation, but we look at what we call the ambiguity function. Sort of what is going to happen if there is a mismatch in the elements that we're going to look at. So one definition, as I mentioned, the ambiguity function for monostatic is well defined, well studied. For bistatic, MIMO, all these distributed is subject to interpretations. So this is one thing that we're going to look at. This is nothing but you have the likelihood, you use this expression, you will find the likelihood ratio of estimating of the likelihood ratio of the parameters here given the measurement. And then we sort of do a mismatch. If this was the likelihood ratio is estimate obtained for a particular theta hat and theta prime, while that, and then you sort of average it over the true distribution. So some sort of like, if you think of Kullback-Leibler and this kind of thing, so it's sort of a mismatched expectation here, and this is what would be your ambiguity function. I'm sorry, this is a typo here. This should be theta theta here, not theta theta prime. So this is the ambiguity function, and then you could evaluate this ambiguity function in this format where you sort of, it becomes now for the Gaussian statistics, the ambiguity function now depends on the Q of theta, which is the covariance matrix of the received signal with the actual theta and also with the estimated theta or any other theta that you would like to put. So now this would be sort of the ambiguity function. And then, Vijay, next slide, please. Vijay, can you go back to the previous slide? There's a question.
Yeah, this NT is the number of transmitters.
NT is the number of
Rn of T.
Yes, this is the number of transmitters.
So this is when the transmitters are perfectly synchronized.
The transmitters are perfectly synchronized in this example. Otherwise, that becomes a nuisance parameter here. But the references are in the slides. If there are any, yes. Now this is the over the distribution of the measurements.
Yeah, so that should also mean to have symbols.
Okay, so
in that sense, you have different symbols.
yeah, as we were discussing, there was a question during the break if I want to use a communication symbol for communication transmission for radar, what would be because the communication symbols are inherently random, so the radar waveform that you transmit would become inherently random. So what is the notion of ambiguity function when you have random transmissions? This is something that bothers the radar engineers because they don't want anything random. So they want to do, because from radar, you know what you transmit. So that's the thing. But then now if you're using the communication system, then your symbols are random. Well, there's no, I would say that there's no, you could argue both ways. That for me, I have to do it on this waveform, on the transmitter waveform. What is the ambiguity function? What is the thing that I get? But then this is not going to be the waveform that is going to be repeated in the next frame, right? So you have to sort of come with a measure that sort of pleases all, and then you add. So this is something that is up for discussion, because radar never used random waveforms in that sense, or random in a sense you use waveforms which are random across antennas, but in time you always repeat.
There's a question on that. So you can use the known communication reference signal for sensing.
Yes, but then that limits the your pilots are about 10%. So that limits the, and then the idea is the longer you use the match filter gives you more gain. So which are next slide, please. So if we were to plot the ambiguity function, this is how it would look like for two geometries of the transmit-receive pair. So you would have the ambiguity function, and then the ambiguity function here, that sort of the target, this is where, if you want to call it more the ambiguity, this is gives you the region of ambiguity where the target could be present, or you could make false detections there. And then when we go to the widely distributed, what we missed in the previous thing is that the ambiguity function is a function of the radar locations. So you could, that opens up the possibility to optimize the radar locations given a particular scenery. I mean, if you without knowing anything, so you could do complete agnostic designs, but that don't give you much information gains. But suppose I know that some information about the scenery, I could do the optimization. Here is another situation where they sort of did a bit of optimization or chose a different set of transmit-receive pairs, and then you could see that the ambiguity function is improved. So there's been some work already in literature on trying to sort of find out how to place the antennas or how to place the radar receivers for particular geometries, one transmit, multiple receive, two transmit, multiple receive, these kind of geometries. I think we put a reference of that, but the idea here is always that you find a cost function. Here we looked at ambiguity function. People also look at Kramer-Rao bounds, and or suppose that it depends on the radar task. So we want to look at localization. So you find the Kramer-Rao bound for the localization, and then that Kramer-Rao bound for localization depends on the radar locations, and then you optimize it. Sometimes you look at single target Kramer-Rao bound. Sometimes you look at two target Kramer-Rao bound, then you get a better feeling. Because if you're having a multi-target Kramer-Rao bound, it becomes quite difficult to handle. So you sort of play around with something that is also mathematically tractable. And then we have the Kramer-Rao bound. In this case, is typically is a matrix. So you come up with some sort of a scalar value representation of the matrix, either through the trace, determinant, minimum eigenvalue. We call it the A optimality, D optimality, E optimality. So these optimalities, and then you transform your problem from the system level to an optimization problem, and then you have a huge bunch of optimization routines that you could use. Okay, Vijay, next slide. I think so. This is where so what happens here is that with multiple distributed antennas, you have the possibility to improve resolution. Because if you just go to the previous slide, 1 minute. Because with you have optimized it such a way that now the ambiguity is only in this region. So you could actually have targets which are closer, but you could still resolve with multiple antennas more than single antenna, multiple radars than single radar. The other issue also, which now become more prevalent, is if you look at it in an indoor sensing situation, you will always have occlusion. So you would have one target sort of covering the other targets. If you're always looking at one view, you would probably miss the other target. Even otherwise, suppose I'm standing like this, that the radar is on this direction, you will not see mostly on what I have on my left arm. So you would need multiple radars, at least even from in that sense, to sort of avoid occlusions. There's also this classical thing in computer vision where you have multiple cameras to avoid. Okay, so but then it's not so simple. There are issues with the distributed systems, and the first paper came out in 2008, and there's not many papers that are in this dimension so far. Okay, Vijay, I think now you can take over.
One question.
Yeah. Okay.
So what sort of synchronization assumptions are typically made with this distributed system?
Neeraj, I think it's pretty much open now because when we started with multi-static radar, that is one of the precursors for widely distributed. There they assumed sort of, you want to call it bit level synchronization. But then there were only few of them. And then they could manage. But in these cases, you cannot, because now we're also going high on frequencies, which are like nanosecond pulses. It's not possible to have. So you'd only have a very coarse frequency For example, the GPS. That's the level of synchronization that we would expect. So in that sense, we cannot do a coherent processing at all. So we have to force most of the processing to be done locally, extract the features to a level where I could do with lower synchronization.
Now in your pictures, I see circles and ellipses. And
Monostatic and bistatic.
yes, and multi-static.
Yes.
So, generating ellipses itself among transmitter and receiver itself means that the transmitter and receivers are synchronous. Perfectly.
This was more, yes, I would, because I'm just putting it as a receive power and then I'm trying to find out where it is. It's R1 plus R2 equals R. That's the thing that we're going to get. Yes, to realize that, we assume that here it's also synchronized.
And it's assumed that the locations are also.
This is under our control. So the whole idea is we sort of design the system. So I know my system. And in fact, if I want to get any information from this radar, from the target, I need, because all I know is a bistatic range, because I know transmitter, radar, transmitter, target, receiver. This is the range I know. So and then I need to know the locations to sort of decipher where the target is.
Just when it comes to resolution, it's clear that MIMO is a winner over the phased array because of the virtual array principle. But now, if you were to look at the detection performance of this MIMO versus phased array, because in a phased array, you are pointing a beam at the transmitter side and channeling the whole of it with a point deterministic target that is clearly. But now, with the scatterer kind of target, what you have shown, a large number of scatterers or the widely extended target that you have shown. Can we say, would there be a trade-off between the diversity gain that the MIMO radar offers versus the conventional detection performance?
No, but if you have multiple, I don't know, sort of here, it's not, I'm saying it's the same target viewed from different angles, right? So I don't know how to, because suppose there's a target here and then I put a beam and then if I turn the beam, probably there's no target there.
Yeah, because MIMO transmitter would make an omnidirectional transmission at the transmitters. And then there are several point scatterers forming a cloud or something.
Yes, correct.
And then returns from all those scatterers are going to come back. Now, we expect a certain diversity gain because of the randomness in the scatterer.
No, I mean, no, there are two different concepts.
Yeah.
MIMO is more collocated. The one that you're mentioning, this is distributed systems. So you get diversity by looking at different, the target from different angles, different positions. So physically you have a different radar system that's looking at the target. So, but of course, there's always a classic, I don't know, Vijay can also explain it better, but the classical radar community is always fixed on beamforming.
Yeah,
And then we have the people coming from signal processing. They bring in y equals mx plus c or y equals ax plus b, and then they bring MIMO radar. And so there's always been a tussle between this and that. And there was an old professor who expired recently, Eli Bruckner. If you search for Eli Bruckner, and then he has made every tutorial he gives is about saying when MIMO radar could be useful and why you should use beamforming. So, Vijay, do you want to answer?
So if I understand the question, I mean, I did not hear the question very well. I'm just going by what you're answering. Could you just repeat the question?
Yeah, so the point is, if we compare the resolution performance of a MIMO radar and a conventional phased array radar, MIMO radar is a clear winner because there is a virtual array forming and then there's a virtual array gain that we see there. Or there is a thinning of the beam due to larger virtual array aperture. But then when we come to the detection performance, phased array radar might do better because there is a transmit beamforming. And the entire energy of the transmitter is just focused on one target rather than spreading it out in an omnidirectional fashion as in a MIMO radar. But when there is an extended real target, like an aircraft or the car that is being shown in the slide here, would there be an additional gain for the MIMO radar due to the diversity of the scattering points in a target? And would that tip in the favor of MIMO radar? I mean, is there a change in the detection performance due to the fact that a real target is always extended and there are more scattering points in a target that would aid detection?
Okay. Yeah, so actually there are multiple aspects in your questions. I mean, we'll just take it one by one. So first is the comparison of phased array with MIMO, but then phased array is already co-located. So we'll compare it with a co-located MIMO first, right? As far as this virtual array comparison is there, so even when we are comparing phased array radar with MIMO radar, we have to be fair to the both, because if you're using the same aperture, same equivalent aperture of MIMO radar, you're using fewer elements, antenna elements for MIMO and more elements for the phased array. But the spatial resolution for that same aperture is same for both. It is same for both phased array. So for example, if I have 20 elements in the same aperture at λ/2 for phased array, I get a certain spatial resolution because that depends on that aperture. Now, within that aperture, if I'm using a MIMO radar, I'll use fewer elements for the same resolution because the aperture is still the same. So the advantage here is for the same resolution and same aperture, MIMO will use fewer antenna elements. That is one. Then, like Bhavani mentioned, Eli Bruckner has written many papers where he essentially argues that, okay, the number of elements are less in MIMO, but the receive processing is more complicated because you have multiple orthogonal waveforms, and that requires multiple matched filters at the receiver, which phased array does not. So you have to take that into account as well, right? You're using fewer elements, but the processing is more complex. Now we move to the target side. So target could be extended or could be a point scatterer. If it is extended, we know it has, you can visualize it as multiple scatterers at slightly different locations, but all near to each other. So let us take just the point target case. In point target case, phased array will be able to track it very well if the target is moving. So the tracking part is very bad with MIMO. MIMO is good for search. You eliminate the entire area and you can do search better. So even though phased array can do tracking better, it cannot identify more number of targets than MIMO. So the parameter identifiability is higher with MIMO radar, lower with phased array, but the tracking performance of phased array is better for smaller number of targets than MIMO. So there is this trade-off. So we really can't say if MIMO is good all the time, because military, even today, does not use MIMO radar. MIMO radar is for civilian applications, for imaging radars, and this is a point of contention between MIMO and phased array community. So yes, I mean, when we are comparing the two, then I don't think even in the co-located case, there is a clear verdict that MIMO radar is really the best. There are all kinds of considerations. So that is about the co-located. Now we go to the distributed case. So in distributed case, you can still have a point scatterer, but then its radar cross section may not be same across all TX-RX pairs. I mean, you don't have to be extended all the time. Even for a point scatterer, the RCS would be viewed differently. It may be very low for certain TX-RX pairs, and RCS may be very high for other TX-RX pairs. Why do we really use this distributed system as far as radar is concerned is, if a target is not detected at location A, but its RCS is still varying for different locations, it may get detected at another location. That is one application. And the second application is for stealth targets where there is literally minimum backscatter. So you send a signal, but you don't get much back because stealth target, they reflect the signal in another direction. Then this distributed system can actually detect it. So spatial diversity could be employed this way in a distributed radar. Now, if you're asking, is there a comparison of MIMO and phased array in distributed way? So yes, I think Kiruba Rajan has done a lot of work where all the transmitter, they may be transmitting the same waveform, or they may be transmitting orthogonal waveform. So you have the concept of distributed MIMO radar or just the multi-static radar. And the same considerations go there, but resolution is difficult to quantify because it becomes more like a statistical definition of resolution. In co-located case, we have well-defined formulae to find out what is the resolution. But in distributed case, we have diagrams like these, where essentially we are averaging over TX RX pairs to find out what the resolution is. So it is very much dependent on the specific geometry. It's difficult to quantify. So there are those kind of trade-offs even in distributed case, I would say. Spatial diversity could be employed by both multi-static as well as distributed MIMO radar.
Thank you. Thank you for the
Okay. Yeah, well, in fact, even when we started MIMO communication, so there's always a region where MIMO is gaining, beamforming is better than MIMO. So MIMO works at higher SNR. Okay, with this, Vijay, I think I'm done here. So we'll leave it to you to go to the next set of slides.
Okay.
There's one more question here, Vijay.
Okay.
What are the parameters that you were getting?
The radar depends on the task that you are looking. Typically localization. So the target location. This example is single target. I mean, as I said, multiple target. The problem is of association. So if you can associate, then you can use multi-target CRPs. Yeah.
So position can be to send signal from with the issue of GDO, geometric variation of precision. So is there any similar issue in radar localization?
Yeah, GDOP is this is coming from the GNS, the GPS thing. I'm not very sure. Is it because of the lack of phase synchronization, or
because of the positioning performance also depends on the geometry, the placement of transmitters.
exactly the same thing happens here. So this is what is the two cases. So this is the ambiguity function. So you could think of it as a localization error in some things. So it depends on the the Fisher information ambiguity function depends on the target parameters, and it also depends on the radar for local locations. Okay, so
okay. So we move on to part 2 now. Okay, so yeah, we are very short on time, but there is a lot to cover. But yeah, these are excellent questions, so please keep them coming, and we'll try to touch upon more aspects on this distributed ISAC in this particular segment. So far we looked into concepts for standalone distributed radar and distributed comms. Now here we bring the two things together, and then we look into some of the examples and what are the issues. So we'll start I'll just summarize some of the issues first that we should consider while designing a distributed ISAC. We'll start with a very interesting application, which is this opportunistic sensing using a communication signal. If you recall, I had mentioned about this topology when we were discussing what kind of ISAC topologies are there or the design configurations are there. So there's a very interesting example which is concerned with weather radars. Then we look into a very general example of distributed Isaac. And each one of these, they are very long papers, but we would summarize them and just to give a core idea of what is going on there. There is a lot of interest in intelligent surfaces these days. So we have done some recent work on IRS-based Isaac. We'll also look into some secrecy rate applications in this distributed Isaac scenario. Then later on, Bhavani will pick up with this biostatic Isaac in a vehicular scenario, and we'll finish it with resource allocation and just a very, very brief overview on a passive distributed Isaac. So we have been discussing about all these considerations in distributed systems, and some of these issues were brought together, were brought up by the audience members in the first part 1 of this tutorial. So here's a very, very quick summary. This is really a subset of a number of issues, but these are some of the key issues that we looked into. And we'll try to provide examples of each one of these cases. So first is obviously the complexity. So if just that nth receiver and m transmitter, just those 2 indices were bewildering for everyone, then when you add communications in the mix, then we have downlink, uplink, you may have multiple targets. So these number of indices in the signal, they just keep on increasing, and it's very difficult to optimize over various considerations sometimes. And again, the question comes to what should be a common metric if I'm designing a system from scratch. So complexity is definitely a very big issue, and it's quite obvious that such a system will be complex. We discussed about synchronization, especially when the platforms are moving. And as I mentioned, you could use GPS for the lower frequency bands, but it has only centimeter level accuracy. So when we move up in the band, then we have to resort to different types of communication protocols. So Rick Blum has written an excellent monograph on various types of synchronization that may be used in distributed systems. So it appeared in, I think, Foundations of Signal Processing journal, I think just a couple of years ago, and it's a very good resource for this. There are also machine learning based synchronization algorithms. So you try to learn it from the data. So this happens a lot, for example, in some synthetic aperture radar applications where the platform is moving and we don't have, especially at millimeter wave, and we don't have a GPS information which is very accurate. Then we resort to machine learning driven platform correction algorithms, which are otherwise done by using synchronization data from GPS. We just discussed there are various statistical design considerations. The ambiguity function becomes statistical if it is distributed. Now, on top of that, if I add communications to the waveform, and I believe there was a question when Bhavani was presenting this, that if I have communication symbols, then how do I get ambiguity function? So again, over there also, because it will become a random function because of these symbols, we take the average, we take the mean of ambiguity functions over several realizations. Now you add the spatial part to this same function, and it is again this statistical definition that we have to look into. So Daniel Foherman did from Washington University at St. Louis. He did a lot of work on looking into the statistical definition of resolution and ambiguity function for distributed systems. For distributed Isaac, there hasn't been a lot of work on this, but there are groups who are working on this definition. Apart from this, the radar, the target channel for radar is also becomes statistical. So as we mentioned that the radar cross-section, when we model it, especially when we are looking into signal processing, it is modeled as a random variable for the distributed radar, and that gives out the algorithms that we want to develop will be based on this random model. Data association was mentioned by Bhavani, so I won't go into a lot into this. We actually have an example later, but just why does this occur is, so if I have a distributed TX-RX system for radar and there are multiple targets, if there is just one target, you will see just one echo at every receiver. But if there are multiple targets, then they are not going to appear in the same sequence in time at every receiver, because some targets may be closer to receiver A, while the same target may be far for receiver B. So if I have 4 targets, 1, 2, 3, 4, their sequencing is going to be different in time. That means they're received differently over the observation period. They're received at different times for each receiver. So it may be 1, 2, 3, 4 for receiver A, 4, 2, 3, 1 for another receiver, and this may be jumbled. So there is a lot of literature on data association for multiple targets and distributed radars. And there are various types of algorithms on how to do this. So that is an additional consideration when we are looking into distributed radar. And if you're doing it in ISAC, then this carries forward. You have to use these kind of algorithms in distributed ISAC. The architectures are also very interesting, and there are various architectures in distributed case. So we can have a passive, most of the nodes may be just listening, and there may be just one transmitter. And the transmit signal may not be known in the passive case. So there are those kind of examples as well. So we have this passive JRC. I think Bhavani will cover a little bit about it later on. We have okay, this was supposed to be the fusion center here. So there's a typo here. So there may be distributed architectures where most of the processing takes place at a fusion center. For example, data association can only be carried out at fusion center because all the receivers are observing the targets in different sequence. So at a fusion, they have to send the data to a fusion center where this association will be carried out. In some cases, we are not interested, we are just interested in just a mere detection and not sequencing the whole thing. And that processing could be done at the nodes themselves. So there may be some sharing involved, what goes to the fusion center and what is carried out at the node, what kind of processing carries out at the node. Now, all of this looks nice, but then we have this situation where we have different types of radars, different types of communication. So in radar, it is not always necessary that each radar within the network is the same, using the same kind of processing, same kind of signal, or even the same type of antennas. So we may have a network where there's a mechanical scanning radar that uses just one antenna, but it is scanning, so it can still get the angular information. And then another radar could be phased array, another could be co-located MIMO. So this heterogeneity in the network is also something interesting. So we will cover an interesting example of this heterogeneous ISAC later. And then with the intelligent surfaces, there are more considerations that are involved. Essentially, IRS may help in non-line of sight sensing or communications. It can help in extending the coverage. It can also help in suppression of interference. There are many benefits. So this is also under this very broad category of distributed ISAC. We can think about this IRS aided system as a distributed system. So let's look at a very interesting example from weather sensing. We'll start from this because I think this is very interesting, and then we'll move on to some of these more complex examples. So here, and this is a very real application. This is a project we are doing with a company that is based in Luxembourg. It is a startup that spawned off from University of Luxembourg. And we work with the data provided by one of the mobile operators in Europe. So the problem is as follows. Typically, weather radars, which usually operate at S and C bands. So S band in the contiguous United States, we have almost 150 such radars. Europe, Canada, India, they are C band radars. So weather radars are very expensive, especially at these lower frequency bands. They are huge systems and their installation cost is high. So it is possible that those weather radars may not be available everywhere, especially in the developing part of the world. For example, even in India, we do not have more than just 10 radars, I think, to cover the whole country, which I think is does not give a very satisfactory coverage. In the US, we have 150 such radars, but then as you move further and further from that actual radar installation, especially after 40 kilometers, the radar beam is already touching the cloud tops and is unable to see what is happening in the lower troposphere, which is where the rainfall phenomena or other interesting weather phenomena like tornado, etc. It all happens in lower troposphere. So as you move further from the location of the radar, for a weather system, it is not very optimal because it starts missing, the radar starts missing most of the interesting echoes at the lower troposphere. So even when I have a weather radar, its coverage is really limited. And in developing regions, we don't have weather radars. So we started looking into this project where the goal is that if we have the satellite user terminals on ground, and the signal is coming from the satellite, so it is indeed passing through the entire atmosphere and then collected by the user terminals, then I can use that information to get some weather information and hence complement the observations that a weather radar is recording for that region. So this is a very good example of communications aided sensing. So here we use the signal from these user terminals, and we'll see in a bit what is the challenge of using those signals. And then we get weather information from there. In the process, how to get that weather information, we also use some information from a co-located radar. That is there's not co-located MIMO, the radar which is located in the same region as these user terminals. And then we try to enhance the weather observations. The advantage of this is that it has a very wide coverage. These user terminals, there are about 300,000 such user terminals spread across Europe. And if you count the number of radars, they may be less than maybe 50 or 60 weather radars throughout Europe. And there are about 2 million such terminals worldwide. So even developing regions of the world have a number of these user terminals. So it's really valuable information that we can leverage for weather sensing. And most of this data that is here at the user terminals, it is just the power that is available. So in a weather radar, we have a lot more information that the radar senses. You can get Doppler velocity, reflectivity, and if it is using two polarizations, which is what most of the modern weather radars in the US employ, US and Europe, and as well as Canada. I think in India, we still use only single polarization. But if you're using multiple polarization, then we get a lot more information. You can find out the size of the raindrop, the intensity of rain, many such parameters are available. But here at the user terminals, we don't have that luxury because it is just one-way transmission that is coming from satellite. And all we receive at the user terminal is the power. We know the power that was transmitted by communication satellite, so we know the attenuation. So here the challenge is how to estimate rainfall from this data, which is the attenuation, or if you know the power at the user terminals, and we already have the information from the COM satellite, so I can find out how much is the attenuation. So we were looking at millimeter wave data here. This is about, I think, 27 to 35 gigahertz range, those kind of bands. And at millimeter wave, an interesting relationship that is very well known is that rainfall estimate, that is this R, it has a linear relationship with specific attenuation. That is attenuation, the derivative of attenuation with respect to range. And we know what that quantity is. So I can use this linear relationship to find out range. And this is the definition that International Telecommunications Union uses very frequently. However, this linear RAH relationship, it very easily gets perturbed if there is, if it is more like a stratiform rain, that is there, the storm is not very turbulent, so we call it stratiform rain, then this relationship is fine. But then if it is a convective storm, then this relationship is no longer valid. So the goal is how to use this data to find out just the AH data to find out R in all kinds of situations. I just gave one example, which is this convective storm, but there are all kinds of weather phenomena when this linear relationship is no longer valid. So here we resort to deep learning because in radar, you don't have to use deep learning all the time. I mean, most of the radars by National Weather Services, they actually use all these other variables, dual polarimetric variables, to very accurately compute the rainfall information. So there we don't need deep learning, but here I have just AH, so I cannot combine it with other variables. So we turn to a learning network where we will train this network on the data from a co-located radar, as well as some in situ instruments. For example, rain gauge, it is an in situ instrument, which is more accurate than radar, but it cannot record information about rainfall spatially, but temporally it is very accurate. And these rain gauges are installed, I mean, it's a very cheap instrument. It is installed by weather services in many locations. So what we did is, we had this in the southwest region of Germany. We have these, what you see here, these black points. These are the user terminals. So it's a very irregular distributed network. We get AH data for all of these terminals. We train a network with a co-located weather radar, the German Weather Service radar. Here it is labeled as DWD radar. And we also train the network with in situ rain gauge data. And then during the prediction stage, we feed it with the AH we get from these terminals, and then we compare it, what kind of accumulation rate, that is rain rate that is accumulated over a period of time, as well as instantaneous rain rate with the DWD radar. So as you can see from these two plots, for just one of these nodes, we are not going to get the same accuracy as DWD radar, but it does follow the similar pattern as the radar sees. And then we combine this information from all the nodes to create a rainfall map. What you see here is a comparison between what the German Weather Service radar sees on the right side, and compare that with what our satellite terminal through all this processing using deep learning network sees. So again, the accuracy is not the same for the satellite terminals, but it does capture the intensity, the pattern of intensity of storm and the direction. So here the storm is moving towards the northeast side. We see this blob moving towards the northeast side. Now we improve this initial estimate by trying many different types of networks and different layers for different storms. And then we came to this kind of a table which compares these different networks. You can use LSTM, CNN, you can use a combination of both, like one for regression, one for classification, and so on. And then we found out that certain networks actually give us lower errors. So this is a tabulation of that data. And then here is a comparison for this big storm that happened in May 2021 in France. So we did this for Germany, France, and Switzerland, 3 countries. So I showed you an example from Germany, then we improved the network and we tried it on France, where there are even more terminals, hundreds of terminals. We use that data. And then here we compare what the radar sees, the Meteo French radar sees, and what our satellite terminal sees. And you can see it very closely matches what radar is seeing. So this is a pretty good result without using these expensive instruments like these big radars. And here is a video of one of these storms, again from October 2020. And you see it captures the circulation. So on the left side is radar, right side is what our network is seeing from the communications user terminals, which have been trained. The network has been trained on the radar data earlier. So it captures the circulation, it captures the overall direction of the storm as well as its intensity. So I'll just let this loop finish. Switzerland was more difficult because it was this mountainous geography, and we're still working on it, how to make it more accurate, because there is a lot of clutter because of the mountains. So we don't have a very good solution yet, but maybe next time when we do a tutorial, probably we have a Switzerland map as well. So, okay, so this was one nice example, a very practical example of a distributed system of communications aided sensing. Okay, I don't know if there is a question. Looks like there is a question.
So the UE should have a satellite link. Is it that not a key restriction?
So they are all getting the, I mean, it's already there. We are using the infrastructure that is already there. We are not, because we are not doing any kind of installation. All of this data is already available, and sometimes it's freely available in certain cases. We just use this data for rainfall estimation, which people had not used before. They were using it only for communications. So yeah, we are just using this for a sensing application. Now, can we do the same with backhaul network? I mean, would you have the data that crosses the whole atmosphere? I mean, from top to down? If you have something like that, yes. Now, there are some other research groups. I think Luca Baldini's group in Italy, where they have used commercial microwave links, not the satellite data, commercial microwave links. So you don't cross the whole atmosphere. The signal does not cross the whole atmosphere. I mean, but it does capture some of the lower troposphere activity. And they have used that to create, to estimate rainfall. So that is another way.
I have one question, which is, this is Ayush from Triple Hyderabad. Just wanted to know,
Yes.
because the UV network that you are using seems quite dense. So which application these UVs are coming from? Like what kind of satellite application UVs these are? That's one that I wanted to know. The other thing is, you said about that you are doing some sort of combining the information from all these UVs. So what's the kind of combining happening there? Like, is it happening at a central location, or like how is that being done? And
Yeah, so yes, indeed. I mean, so for example, I think I mentioned here. Yeah, here, the signaling data is already aggregated in some kind of database. So you see there is like a hub, you know, where we get all the information from these user terminals. And once we have that, so what do we actually do? For each user terminal, we get the rainfall estimate. So what you see here, for example, plots like these, instantaneous rainfall and the accumulated rainfall. So for people who are not familiar with weather radar, instantaneous rainfall is not a very useful metric for quantifying weather because it is extremely variable. So we typically look at the accumulated rainfall data over either few hours or days, and sometimes even weeks. So this is more accurate. So for each node, we compute this kind of data. So for each node, I know what the rainfall is, but it is only in one direction, right? I mean, radar can capture spatially a lot more, but the nodes are only looking at this particular point, right? So what we do is we get this rainfall data at each one of the points, and then we interpolate in the map. So what you see here is this interpolation of that information across the map. Now you can use some simple interpolator, or you can use a learning network, which does regression to actually interpolate across a full area. And then you create these rainfall maps. So if you talk with meteorologists, they always trust radars. And of course, we also trust radars. And as a radar engineer, of course, I would trust radars because it is observing at each and every location. Satellite nodes are not observing at each and every location. They are interpolating at the locations where there is no data available. But this kind of application is useful when the radar, when the, like I said, as you move away from the radar, the signal becomes very weak, and maybe you're not getting any kind of echoes from lower troposphere. So at least this satellite data may be used to complement what weather is observing.
Thank you.
Maybe to add, it's a VSAT network.
What's a VSAT network?
It's a VSAT network. And then the one in Germany is a managed network. In Germany, that region of Germany is hilly. So what has happened is that the company puts a VSAT in the village, and from the village, from that you have connection to the houses.
And these are VSAT which are talking to geostationary satellites?
VSAT to geo, and the VSAT every 5 minutes reports its SNR.
Okay.
And so that's all collected at the central, because you use an operator, so he collects everything and then he gives us this.
Okay, there's another question. Why is LSTM needed? So, I mean, there is definitely temporal connection. I mean, you're getting rainfall or weather. Weather is a connected system, both spatial and temporally. And there is this spatio-temporal variability that different types of instruments they try to capture. So yes, there is temporal relation, but we are not saying that LSTM is needed. You can see from this result that LSTM is not always good in all the cases. So we tried different networks. Eventually, we decided to run multiple networks in parallel, and then we decided to take the average output from all the networks. And as you can see, some of these combined cases, they actually give us better information, because even CNN may fail for certain networks. And what this shows is that for this system, which is so much variable, there is variability in both domains, spatial and temporal, it's very difficult to capture that kind of information through just one network. So we would like to use a combination of this, and our research shows that a combination is usually better than using just one of the networks. Okay, so because we do not have much time, actually, it's just 20 minutes. Let me quickly give some examples at least, and then we can have some discussion later on, because there is a segment that Bhavani also wants to cover. So I'll quickly touch some examples just to give a highlight of what all we do in distributed cases. So we look at a very general case of distributed MIMO radar and full duplex multi-user MIMO communications. And here we are doing co-design. So we are designing radar waveform precoders for UL and DL, as well as the receive filters for radar and comms. So this is the system that we use. First, we look at just a single target scenario. So we have multiple radars, multiple transmitters and receivers for that, several of these downlink and uplink UEs. We also have clutter in between. So like I said, if just using two indices for TX RX pair was so difficult, now imagine with this kind of a complex system, we have even a lot more indices to keep track of. And then you add full duplex to that, you have self-interference as well. So it becomes very, very complex. But in this paper, which has been accepted in Transactions on Aerospace and Electronic Systems, it's a very long paper where we look into this in a very systematic way, this very complex model. And here we use this in-band MU MIMO, so we have this self-interference as well. So here we started with, this was the system model, and then we looked into a common metric to design these four quantities that I mentioned, that is precoders for both ULDL, the receive filters, and the radar code matrix. To design all of them, the common metric that we use is based on mutual information, which I had referred to in the first part. But we changed that mutual information a little bit. We proposed a new metric, which we call as compounded and weighted sum mutual information, which combines the mutual information from radar as well as comms. And then we put some constraints on this. So you may have a power budget. There may be rate constraints on the waveform. You may have power constraints. So the problem obviously becomes very complex, which we then solve through iterative methods. It's a highly non-convex problem, so we try to relax it and then solve it sequentially. So this is the transmit signal model. So don't worry about different indices. Let me give a brief idea about this. So in the transmission, obviously the radar is not going to transmit at the same time as these communications frame. So what we assume here is we assume some basic unit. So what we say here is the pulse width of the radar. We say it is equal to the symbol interval for communications. And then in the same observation window, we get equal number of these pulses and equal number of frames. That is one assumption we start with. Now you can have unequal number, it will become even more complex, but just to keep things simple, this is the model that we chose. So you can write down the transmit signal equations. After that, when you look at the receive signal model, even more complex. So at the base station receiver, we get our uplink symbol of interest, but then there's a lot of interference. There's interference from radar. There is self-interference because of full duplex. There is multi-user interference as well. Same at the downlink. So you're seeing multiple terms here and plus noise. So this last terms, they are, that's a noise term. All kinds of interferences. And at radar, we have the target, the reflection from the target, but then the downlink signal also gets reflected from the target. So we get that as well. You get clutter as well. If there's a collocated clutter, you'll get clutter signal. And then we have this noise as well. So for radar, we are only interested in the target, and everything else is basically interference plus noise. Even clutter is combined into that. And then, so at both communications and radar, you get a lot of information that is not desired. In this particular case, apart from the co-design, we are also interested in cooperation. So if you recall, I had mentioned spectral cooperation as one of the topologies. By that, what I mean is that at the radar, I can utilize the signal that is reflected back from the target, the radar signal that is reflected back from the target. But there's also downlink signal that is reflected from the target. And if I can utilize that, maybe I can enhance my detection probability. So we do that here. We also utilize the downlink signal for the detection of the target. And then, as I mentioned, we use this common metric. I mean, we essentially weight the mutual information from radar and comms and come up with this combined metric, which we call as compounded and weighted some mutual information. And then we try to maximize it subject to all different kinds of constraints, and the variables here that we are maximizing it over are the radar waveform, U are the receive filters, and P are these precoders. And there's not just one or two nodes. I mean, the waveform code matrix, we have MR transmitters, U, which is the receive filters, is both radar as well as comms, and there are so many receivers, so it's very complex. And then we have power budgets for uplink and downlink. There are rate constraints, and then for the radar waveform, we also put the power constraint. So extremely complex, but that's what our paper is about, and we use block coordinate descent to solve this problem. We do this in different steps. So in the interest of time, because I want to cover some of the other things, I'll give a very brief idea on how this is done. So we first tackle this problem without the power constraint. And the trick here is we utilize this relationship that Professor Rick Blum from Lehigh University had come up with, where you can convert the mutual information, you can relate it with the MAC. And then the rate constraints, we linearize them later on in the same problem. We linearize it with respect to the precoders. You take the Taylor series approximation, and then we solve that problem first. Afterward, the estimate of the radar code that we get, then we use this matrix nearness problem to solve for the radar code given the power constraint. So we separate out the constraints in these two problems, and then we iterate between the two problems. That's the goal. And in between, we use all these different types of relationship to go between the WMAC and rate, to between the mutual information and MAC, using some of the standard results. So here is what I just explained. So we have this, now we have converted the problem to this WMAC minimization. So maximization of MI, we convert it into WMAC minimization problem. We remove the power constraint. Now we are just solving it for PU and some estimate of A. So here is the flow of what I just explained. I'll skip this because otherwise we are not going to cover some of the other interesting things that we have. And then we iterate between these problems. So here are some results. So once you get this optimal waveform, precoders, and filters, you try to use that, and then in this target scenario, then we compare with cooperation and without cooperation performance. So if you focus on the second plot, which is what we call as receiver operating characteristic in radar, which is a plot between probability of detection and probability of false alarm, then when there is no cooperation in such a complex system, the probability of detection is this curve, the dashed curve. But if I can use this downlink signal, so in this distributed scenario, this is actually pretty bad. It's not very, from a radar engineering point of view, this is a very bad detection curve. But if I could use cooperation, that is the downlink signal, and I optimize my design variables through this method that I just explained, then I can bump this up in this region. So there are these other curves that we are comparing it with, but then we assume that there was no radar there was no interference from certain directions. But overall, the interesting curves here are this dashed curve and then that solid black curve. So with cooperation, you can improve the performance at the radar side. And then the same thing we do for this, how our matrix looks like with our proposed waveform and precoders. So the CWSM is much higher with our proposed waveforms, precoders, and filters, because obviously it was optimized for those variables compared to some of these standard waveforms or conventional precoders. Then here we compare the full duplex performance as well in the presence of self-interference. And again, the proposed scheme actually gives a better performance. Then we also did this for multiple targets. And as I mentioned, we have this data association that you have to do in multiple targets. So first you complete your detection at each and every node, but then in multiple targets, the sequencing is all garbled between different receivers. So we need to apply these are standard algorithms, but when we use these for integrated sensing and communications case. So there's this famous algorithm JPDA, which gives you the association probability for different targets. And that's how you can correct the sequence. So we will not go into the details of this. Information is there on the slide, but let me show you one result. So as the number of targets are increasing, so we go from 2 to 6 targets, and we plot the probability of correct association. So even though this looks like it is going down, but it's 0.96, which is actually pretty high for probability of correct association. And this is when we use this optimized design that I just mentioned. That is, you optimize over precoders, radar code, or filters using this CWSM metric. Then you get such a high probability of association. With anything else, this comes down drastically. As we saw, the PD had already come down at every node. So association will be even worse in that case. So, okay, this is a conclusion. I think I've already explained what is the larger idea here. So I just want to ask Bhavani, because we have very little time. I mean, either we can get some extra time if it is possible, or should we skip some of the content and you want to focus on some of the other things later on?
You can go over 10 minutes.
Hello?
Maybe go 5-10 minutes over time.
Okay, so I'll then take maybe 5 minutes, and I think this is one of the last segments that I have to cover, which is with intelligent reflecting surfaces. So I'll give an idea of this, and then I think Bhavani may need maybe 10 more minutes, something like that. So, okay, so now we look into intelligent reflecting surfaces, which a number of you might have heard about, at least this term, if you have not worked in this area. So in electromagnetics community, we have been dealing with a lot of developments in intelligent reflecting surfaces for a very long time. So starting from around 2006 or 7, Professor David Smith from Duke University, he published a lot of papers on what we call as metamaterials, which are synthetic materials. They are not found in nature, and they provide a greater control over electromagnetic waves. So that was the idea. And if you search for some of the articles that were written at the time in the mainstream media, it was about, oh, the Harry Potter's cloak has finally been realized. That's how it was portrayed. Of course, we cannot still make that cloak today. It was a very limited result that they proved in their paper in Science journal. Then fast forward by many, many years, and communications and radar community, they are using these surfaces which are composed of metamaterials. Essentially, they have these what we call is their constituent elements, which are these metamaterials based elements, which are located at sub-wavelength spacing on this two-dimensional surface. So the meta surface is a two-dimensional version of metamaterials. Metamaterials is 3D. If you take its two-dimensional version, we call it a meta surface. And inside that, there are all these constituent elements. Each one of them could be programmed individually and gives you a lot of control over the electromagnetic signal that is emitted from that surface. So if we are using a radar or communications application where we do require a particular shape of the beam, then this kind of surface could be very useful if it is used as an antenna. So in beam forming, you can perform with the same surface. You can have beam steering, you can steer the beam, you can have multiple beams, or you can have an adaptive pattern. With the same surface, you can also do different types of modulation, as one of our papers shows that you can, with the same antenna, we are doing frequency modulation, phase modulation, and polarization modulation. So I mean, maybe at some other time when I'll do a tutorial on intelligent surfaces, then there we talk about this polarization modulation technique, which intelligent surfaces can actually enable. As far as its difference with the conventional system is concerned, even though we are calling it as this intelligent surface, you have to remember that everything that a phased array does, intelligent surface aided systems, they do exactly the same thing, except that in a programmable, this intelligent surface or programmable meta surface, the RF circuitry is integrated with the antenna. So on top, what you see is the conventional wireless transmitter, either for comms or radar, and the receiver would be similar. At the bottom, what you see is that the RF parts like filter, mixer, PAs, they are all integrated with the antenna, and it is programmable. We can digitally program this. So it's not like that with intelligent surfaces, we are gaining new functionalities. The functionalities is still the same, but then we are reducing a lot of hardware at the back end. And this is very useful for military applications or applications where size, weight, area, power, all these constraints are there. For example, autonomous vehicles or drones or satellites. This kind of surface could be useful. So the research is still ongoing. We don't have a lot of these functional surfaces, but there are some commercial solutions that have become available recently with a lot of restrictions. But on the signal processing side, this is quite interesting because we can use it in two ways. Either you can put it at the transmitter and use a separate feed and then digitally control this to carry out various types of modulation and beam forming applications using the same surface. Same surface does so many things. But if I had this separate hardware, then I can probably do just one kind of modulation because the hardware was, this actual physical hardware was designed for that kind of modulation. So this is very useful in that way. Another way is, which is how we use it in ISAC, we use this IRS as part of the channel. So it is not located at the transmitter, but somewhere in the channel. And it is largely passive in this particular application. That means it just deflects the incoming signal in a desired direction. So it could be used in cases where there is a blockage between the radar and the target, or the communications transmitter and the receiver. So you send the signal and IRS actually reflects it in the desired direction. And hence you can use it to enhance your coverage. You can use it for non-line of sight sensing slash communications. And there have been some works where this particular surface may be not completely passive, but may have slightly more active configurations, and then it gives us some new kind of applications as well. So we have this recent work where we used multiple IRS. That means you don't use just one, but there are multiple IRS at different locations. So it's, again, this distributed kind of system. And then we try to design the phase matrix. So in IRS, the design parameter are the phases of different elements. So we just model it as a matrix with either discrete or continuous phase values. So we try to design this phase matrix, and then the usual Isaac parameters, like we may have a beamformer at the transmitter, which may want to co-design with this matrix phi, which is the IRS phase matrix. And we did this for a wideband model. That means we use this OFDM system, and people who are familiar with the beamforming there, we have a frequency-dependent beamformer. You can't use the same beamformer for the whole frequency in a wideband system. So we have this FK, which depends on the kth subband. So here is the transmit and the transmit signal from a common transmitter, and then what is received by the radar. Here we include both the LOS path, if it is available for a target. Then we use the LOS path, and if it is not available, then we use the NLOS. In some cases, you may want to use both to enhance the detection. So we model the received signal by considering these cases. Again, a lot of indices here, mth IRS, kth subcarrier. So the model is quite complex, and same for the communications. And then when we want to formulate the problem, we look at the SNR, we consider clutter and noise, SNR in both links, communication and radar. Now, as I mentioned before, you have these two systems, you need a common matrix. So we use this kind of a common matrix, which is kind of a weighted SINR. And this is a radar-centric problem. So we decide some kind of minimum communication SINR, and then try to maximize just SINR for the radar in a reformulated version of the problem. And it is non-convex. So again, we use some kind of iterative methods to solve it.
What is VM here?
That is the phase matrix of mth IRS.
Oh, very good.
Yeah.
And in the SINR expressions, one of them has two phims in the numerator, and the other one has only one phm. Like the radar one has two phims in the numerator.
Yeah, so this is because the signal goes from IRS to the target, comes back from IRS to the receiver.
Oh. Right.
And so this is a I would say a toy version of the problem. If you look into our paper, there are many more paths, right? It can go from the IRS to the target, come back from the IRS to the target, or come back directly also if the direct path is available. So you can consider all these kinds of permutation and combination, and then try to optimize it. So in our paper, and if you have multiple IRS, it's even more complex. So in our paper, you'll see a more complicated expression than this one.
Okay, thank you.
Okay, so this is our, like I said, we solve it iteratively using ADMM and then Dinkelbach algorithm. Again, I'll skip the details of this. You can see in our papers, we show the convergence of the algorithm, but a more interesting result is here. So if I'm using two IRS, like more than one IRS, our result actually shows that, yeah, you can improve the radar SINR. But if you actually optimize this further, then the result is even better with optimization. If you're just using random phases, for example, you compare it with that, and then you compare the optimal version of the phases, you can improve it. Now, here, obviously, we have not considered the interaction between different IRSs. So the idea here is that when IRS reflects a signal towards the target or towards the receiver, desired receiver, it is not sending that same signal to another IRS. So the interaction between IRS is not considered. So, and why is it so? Is because we consider that different IRS, they are separated enough so that the signal is quite weak from one IRS to another. Also, the IRSs, they are beamforming in the direction of target and direction of receivers. Then again, that signal is going to be very weak. And this is what, if it is an intelligent surface, you can assume something like this, that it actually does not transmit in undesired directions. And it's not completely implausible assumption, because as I mentioned, when you have metasurfaces, you can have these adaptive patterns. You have a greater control over what kind of beam it should be. So we consider that assumption in this work. Now,
in the previous slide, the optimal T curves are actually below the T equal to 0 curves, right? Is the legend? Yeah, what is T here?
the T is actually this auxiliary variable. T is the auxiliary variable. So
T is the quality of service you want to give to the communication.
Yeah, greater than or equal to T.
Yes. So
Yes.
if T equals 0, that means I don't care about the communication. So the
So
radar
radar
will go
will be
back.
better. Good. Understood. Thanks. Yeah.
okay, so what I presented here is actually a subset of what is there in our paper, but I think it gives an idea for this IRS. The next one is also IRS, but then this is a secrecy rate application. So I'll just give a brief idea, and then I think I'll hand it over to Bhavani for the next segment. But I'll just explain this problem because it is a very popular problem in joint radar communications. And the idea here is as follows. I have, so if people who are not familiar with the secrecy rate problem, usually we have a transmitter and a receiver, Alice, Bob. Alice is the transmitter, Bob is the receiver. And then there is an eavesdropper, which is listening to those messages. So goal here is to actually minimize the information that goes to the eavesdropper and at the same time maximize the information that is received by Bob so that Bob is still able to decipher that information. So there are many variations of this problem in communications, secrecy rate communications. In DFRC, people have been looking into a version of this problem where the eavesdropper is at the target location. Now, this presents a very interesting and contradictory scenario. In order to detect the target, I must transmit this common waveform, which has communications information, at a power which is high enough so that I get my backscatter to be able to detect the target. Backscatter should be strong enough. But at the same time, if I transmit it at a very high power, there's a danger that the eavesdropper, which is co-located at the target, is able to intercept the communications message. So there is a trade-off that which is this SINR or power trade-off, that we want power to be above certain level so that I detect a target, but also below another level so that eavesdropper is unable to decipher this common message. So there have been many, many works, mostly from Andrew Jung from Sydney. They have done a lot of work on this. Nasser Hassanen and Moinis Amin have looked into this. Jonathan Chambers in UK, they have also looked into some versions of this problem. Then we started looking into this problem in the presence of IRS. Can IRS actually help in this problem? Because you can probably have a better trade-off if there is an IRS in between. So the first version of this problem was again by Jonathan Chambers, but they looked into only a single IRS, and they did not consider multicast communications. They looked into only unicast or broadcast versions. So in this work, which appeared in this year's ICAST, we look into multicast case with multiple antennas. So this is MIMO DFRC or MRMC. And we also look into multiple eavesdroppers. So far, most of these works are for a single eavesdropper and single target, but we look into multiple eavesdropper, and we consider both direct and indirect paths from IRS. So we consider that there are targets for which LOS is available, So we partition the targets into categories in this problem. There are targets for which LOS is available and is very strong, so you can ignore the NLOS path. There are targets which are blocked, their LOS is blocked, so we only look into the NLOS. In the previous version where Chandra had asked this question, why you have two phi, there we were always looking into both LOS and NLOS for all the targets. So if it is available, both paths are available, we actually optimize over both the paths there, but here we partition it just to make the problem simpler. And then
so here in this IRS, what you have showed is mostly increasing the signal strength. So apart from that, is there any advantage of IRS in terms of localization performance, precise localization performance? Will it provide any other degree of freedom?
So I mean, I did not say that IRS improves signal strength, because IRS, the signal that is coming via IRS will be actually weak. But if you do not have LOS path, so LOS is always the stronger signal, right? The line of sight. But if LOS is blocked, then and if I have IRS installed, I still get some signal, but it is weaker. If I have both paths available, then LOS is sometimes so strong that you actually don't need NLOS. However, in radar, as we know, the received power, it varies as the inverse of fourth power of the range. So it drops very quickly, right? So if I have a target that is very far off, the LOS may also be weak, but and NLOS will be even weaker, but the combination of those two may give me enough strength to actually detect it, which I may not have detected using just LOS. So that's the first thing. It is not all, it is actually not a strong signal. It's a very weak signal, but if you combine it with LOS, it may either increase LOS strength, or if you're able to detect that weak signal, you can detect the target for which LOS was not available. So that's the first part. The second part is what are other applications? So we are enhancing the coverage. Coverage enhancement is one of the major applications of IRS. You are enhancing the coverage. In some cases where coverage is not enhanced, but you are getting these both signals, you could probably use it to enhance the detection. In other cases, you can also use it to suppress interference, like clutter signal may also come via IRS, but if IRS has some more intelligence built into it, it can actually attenuate the clutter signal while reflecting this overall signal towards the radar. So many such applications. In secrecy rate, we use this to actually, again, enhance the coverage, but here we are using the IRS phase shift optimization such that the secrecy rate is maximized. Okay, any other question? Okay, so I think there's a good time for me to stop, but I do want to show one plot. So again, we do this model, and then we have this problem, secrecy rate maximization problem. Actually, this objective function that you see here, its format is very similar to what you see in standard secrecy rate optimization. So what we do is you take the kth eavesdropper, and like I said, eavesdropper is co-located with the target, and then you take one of the users. You find out the difference between the rates between both of them, and you take the minimum of that difference. Our goal is to maximize that minimum. So this is the secrecy rate maximization, very standard formulation. But then we subject it to these power constraints, because like I said, it has to be higher than certain power so that the targets are detected, which are these two cases, these two constraints that you see. It is higher than certain power, and we do it for direct path. Like I said, we partition the targets into two parts. One are the direct path and one are the indirect path. We are not considering the case where both paths are available for a particular target, because if the direct path is there, our assumption is we'll just use the direct, it is the strongest path. And indirect, we only use when direct is not available. So we have those two constraints, and then we have this first constraint, which is that it should be below certain power so that the eavesdropper is not able to intercept everything that is there in this joint waveform. And again, there's a non-convex problem. We solve it through in an iterative way. And then here's the result that we get. So with multiple, yeah.
I think regarding a problem formulation. So how are these power boundaries determined?
So we start with some, I mean, because we are not optimizing at P and gamma K, we decide with certain values that it should be lower than this. And then it really depends on what kind of, because these are constants in our case. We are not optimizing on this. So you see, if you can be higher than certain power. In practice, we know how to determine this. In practice, there is always a maximum power that you can transmit at any frequency, right? Which is decided by the FCC limits that you cannot transmit above certain power. So you always know what is the max you can transmit. And then the minimum is decided by what kind of detection I want. So if you look at radar equation, you have the minimum detectable power mentioned in that equation. So you can determine the minimum detectable power there, right? So using those kind of standard theories, we determine these constants. For this problem, we assume that, okay, there are certain values, and at least in the numerical experiments, we start with some known values and try to optimize what kind of W and B we can get. Okay. Yeah, so here's the result that we get with IRS and without IRS for 1 and 2 eavesdroppers. So as you see that with IRS, we are able to maximize the secrecy rate that we get is actually higher than not using IRS at all. So, but just to answer another question that was asked, so IRS could also be used in this specialized application of secrecy rate maximization to get a better performance. So we have, and this is again in a DFRC scenario, I think this is more interesting from secrecy rate maximization point of view, because we have these very contradictory constraints. And I believe there are now new versions of this problem for, let's say, arbitrary channels. I think I have seen some works on this. So I think it's a very interesting area if someone wants to pick this up and extend this with IRS. How do we do the DFRC secrecy rate maximization? I think at this point, so Bhavani, I'll defer to you, but I don't know how much time we have. You may need maybe 10 minutes.
I will just sort of say that not everything is wiki-dory with JRC, because one thing that we have been looking throughout the thing is that there is a trade-off. There's always been a trade-off between like person who? Okay. Yeah. There's always been a trade-off between radar and communication. And in one case, this is the case where actually they don't exist together. I mean, you can show through fundamental bounds that in a bistatic case, you cannot have joint radar and communication. So there should be some sort of multiplexing. So which I can quickly go through. I will just mention this and then we could close. Yeah, this is the one that we are looking. The idea here is that just that the red car wants to transmit to the gray car, and then the gray car also acts as a radar receiver. So it's a bistatic radar system, and then you have a classical transmit receive path. Next slide, please, Vijay. Yeah, so we just look at one signal here, which is we just look at the phase modulated continuous wave signal, which is nothing but a CDMA code. And then this is a waveform, radar waveform that people are now using or being sort of used for interference mitigation. So this is the radar signal. And the other one that we used was OFDM, but we could skip that for the time being. I'll just focus on the PMCW. This is the radar signal. And to convert this radar signal, next slide, Vijay. So to convert this radar signal into communication, all that I do is follow the CDMA system. Here I have the DPS scale, is not worry about the differential part. It's just simple CDMA system to convert this PMCW to JRC system. Okay, so I then use multiple antennas. It's immaterial here, but I transmit, and then I would have the target, so I would transmit as I get it, and then I would get the signal is backscattered. So this would be the transmitted waveform, and then this would be the waveform at the target. So you would have the delay, then you have the Doppler versions, and then you would have the beamforming weights from the multiple antennas, and then the communication symbol. So if you look at the indices over which it varies, M is what we call the slow time. So it varies chirp by chirp. So it's a slow time. And then the chip here, the CDMA sequence varies in fast time. So it varies, as the name suggests. Next slide, Vijay. So I think you just have to click, and then, you go on doing everything. You write down the transmit signal, you go to the receiver side, write down the receive signal, do the filtering, remove the baseband, and then do the filtering, and then finally we are happy to write it in terms of some matrix. And then when it's written in that form, we are all in sort of comfort zone. But this would be the signal that's received. I put it in a time space, in a time mode for different antennas. Here for the pth antenna. So if you look at it, you would have the beamforming weights and then some channel weights. But then this is the diagonal matrix which contains the channel information, the communication information, and this is the Doppler here. This is the Doppler information. Now, if you look at it, both of them are diagonal matrices, and then both of them are getting multiplied. Now, if you are supposed to use a PSK signal, for example, then everything is in the phase, and then it becomes unambiguous. It becomes ambiguous to understand what is Doppler and what is the communication signal. In the sense that the communication signal and the Doppler both change in the same domain. Okay. So next slide, Vijay. Yeah, the same thing happens in OFDM if you were to do. So you would have the range is obtained from the thing. So the range and the communications, the range and the communication symbols sort of bring ambiguity into the system. But I think we can go to the next slide. I think we just mentioned what would happen. Okay, so now if I want to look at a Fisher information matrix, now at the gray card, at the receiver, it has to estimate range, and we can forget range, Doppler. If you can forget the angle for the primary range, Doppler, and the communication symbol. There's a three element vector, and I find the Fisher information matrix of that, and then it turns out that the Fisher information matrix is, for the scheme that we are looking at, the simple extension of the data string is that it is rank efficient. That means you have problems with identifiability. So in particular, you could see that for one particular transmission scheme, the Doppler and the communication symbols couple, for the other, the range and the communication symbols couple. So no matter what, you cannot sort of unambiguously get this information. So only thing that sort of remains is to do multiplexing. We use some portion of the waveform for radar or communication to get information, and then bootstrap it, and then try to use the other portion of the frame for JRC. And this, however, the joint system. So this is a very simple case of not monostatic but distributed system where the radar receiver and the communication receiver are co-located, and then they want to get more information about the environment and also the communication. You cannot do it simultaneously. So you have to do some sort of orthogonal allocation of the resources. And then when you do it, you would get all the information available. Okay, Vijay, I think we can, this is the information that I wanted to say, that not everything is, when you have the hammer, everything shouldn't look like a nail. So it will not, JRC has its limitations. And then the other question is, in these cases, you cannot do anything, but in the other cases, what is a good method of comparison? Because there's always a trade-off. Should I compare with a system which was only for radar or only for communication, but now I'm bringing both the functionalities? Of course, you want to take it. So that's the thing. And then the idea here is to, I'm using all my mails now. Vijay, you stopped sharing, I guess.
No, I'm sharing.
Okay. I think we can go to the summary slide. And there is another example that we can skip all this. We can go to the summary slide. We also did a bit of heterogeneous network optimization.
Yeah, this was, I think, the last example, but I guess we can skip this because I did mention what heterogeneous network is, like you have different types of radars. So should I just skip this, Bhavani?
Yes, I think you can skip this part.
Okay.
This is one which has a lot of optimization involved, so people who like optimization.
So by the time I reach to the last slide, I think you can probably mention a little bit what did we do in this. This was also tracking, right? So we haven't seen any tracking examples so far. There was also tracking in this. Let me see. It's a lot.
Okay, I think you get everything now. It's
I'm trying to see. Okay, and then okay, passive case. Okay, summary.
You want to summarize, Vijay?
All right. So we start from like the first slide, if everyone recalls, where I had mentioned a number of issues in distributed system. I think through these examples, I hope it is clear to the audience that a distributed ISAC is indeed very complex. So ISAC is already a complex system, and there's so much work going on. We are focusing on distributed ISAC because it is driven by a lot of practical applications. So sometimes the applications are these communications aided sensing, where we covered this case of using distributed satellite user terminals to complement the observations of weather radar. Then we looked into a very general distributed system where we have multiple user equipment. We have many different transmitter receiver of distributed radar, all with different kinds of constraints, QoS constraint, power constraints, etc. And then we looked into that optimization, how complex it is to solve something like that. And there could be many variations of that. Like, for example, you can have a full duplex system. So we consider that as well. Common metric, like I said, is always an issue. You can either combine some kind of weighted metric. For example, we saw in IRS-based system, we were combining SINRs, or we were trying to make it just radar-centric or communication-centric. We saw use of mutual information, which may be used as more or less like an equally weighted metric for both systems. But again, I won't say it is the best solution, because as far as radar is concerned, very hard to make a connection with mutual information and exact a very precise radar performance. But those are some of the solution paths. And the key issues, like I said, so one is these performance matrix. Synchronization, we did not cover a lot, but it is definitely something of interest. Some groups have looked into it very briefly. There's also issue of deriving low complexity algorithms. So if you have data association and all these different processing nodes, you may want to look into reducing the complexity at the receiver. We did not consider resource allocation, but obviously if so many systems are transmitting at the same time, they may want to share the transmission slots, or sometimes bandwidth we have already seen. But in the tracking case that we did not cover in detail, we also look into resource allocation of power, bandwidth, and transmission slots between these heterogeneous systems. So to summarize, this is a very rich area for signal processing practitioners. I don't think there is a lot that is published on distributed ISAC. This topic is more or less just 2 or 3 years old. It's fairly recent. So it opens a lot of new applications. And yeah, we would like to, we have this book coming out later this year, which covers a lot of other interesting aspects by about 40 or 50 researchers in this area. And you will also see some discussion on distributed case there. For the biostatic case, we have this overview article in Signal Processing magazine. If someone is interested in just biostatic millimeter wave joint communications, I think this provides a very good overview. So with that, I would like to thank the organizers for giving us an opportunity to share our research. And thanks to the audience for your patience. It was a very long tutorial. So I hope everyone is happy at the end of this, and we are able to impart some useful information to all of you.
I would also say that this is a classical example of trade-off. You overshot, and so you're losing your lifestyle. So thank you very much.
Thank you, Vijay and Bhavani, for a great overview of recent work on ISAT. And yeah, I guess we'll be looking forward to the upcoming book. So let's thank the speakers once again.
Take it back and give it again.
So Vijay, sorry, you're not going to get this. Huh? You can see here.
What is it? What is it? Is it a perishable commodity or unperishable commodity? Okay, yeah, I see that. Okay.
Thank you. Thank you very much. The slides you will distribute.
Thank you, Vijay. We are signing off now because we have to rush for lunch and rush back.
Okay, great. Yeah, thank you. Bye-bye.
Yes, to sleep. And you should sleep now. Yeah.
There are 2 transformers which are taken to the main guest house. There are TVs that are available.
ಇದನ್ನ ಕಿತ್ತಿದ್ರಿ ಅಲ್ವಾ ನೀವು?
ಎರಡು ಹಾಕಿದ್ವಿ ಸರ್.
ಅದು ಇನ್ನೊಂದು ಅವರು ನೀಲೇಶ್ ತಗೊಂಡು
This one.